We will describe the image of the band face detector type CDR in several videos. Even though the band CDR simplifies the design changes and works robustly over PVT in any high-speed SerDes, the band CDR is difficult to analyze the root dynamic behaviors due to its nonlinear properties. In this video, we are going to show you why we need a band root dynamic analysis over phase tracking modeling in a band CDR design. As usual, before looking at all the caveats, let's look at the ideal phase tracking should be. As you can see, any sinusoidal jitter at the TX output over RX input could cause the RX to make a wrong decision or increase the bit array in the link due to the less timing margin of data sampling. So we hope the RX can track the sinusoidal jitter perfectly, such that the TX jitter doesn't hurt the bit array at all. For example, the phase error between the RX input and sampling clock is half UI, such that the data was sampled at the middle of the eye, which is the maximum timing margin. Since the sampling clock and the recovery clock could be out of phase, we should expect the phase error between the RX input and recovery clock to be nearly zero as well, which is showing in our phase tracking modeling in a band CDR design here. Therefore, in the following images, I will show the relationship between the phases of the RX input data and the recovery clock. Alright, after understanding the ideal phase tracking, think about the real phase tracking images for 5 seconds. Bingo! The band CDR may result in a limit cycle at a steady state, which would have a non-zero phase error between the input data and recovery clock, and then reduce the eye width margin and the corresponding bit array increased. Please be advised that all the phase tracking images come from our simplified phase tracking modeling of a band CDR, which will show the band root dynamic behavior precisely. Let's start with how the limit cycle behaviors came from, such that you will appreciate all the images provided by the phase tracking modeling here. Think about the root causes of limit cycles for 5 seconds. Correct. If the phase correction of the band step size of the band CDR is too little to track the movement of the input phase, the output phase movement of the CDR must be Fourier limited and result in a limit cycle. In this example, we put a 1/10 band step size of the original design. Then the phase correction was not big enough to catch the input phase quickly. So it's expected the phase of the output recovery clock is Fourier limited. What else of the input phase can cause the Fourier limited? Think about the slope images for 5 seconds. Right, the opposite image of the little band step size of the band CDR is that the input phase step could be too much. If the amplitude of the input phase movement is too big, the CDR will be Fourier limited as well. In our modeling experiment of making 4 times phase movement over 4 times peak-to-peak jitter amplitude, the phase tracking image not only shows the limit cycle, but also provide the phase error could be up to 40% UI here, which is very serious and could cross the eye width at the sampler input completely. What else of the input phase can cause the Fourier limited? think about the slope images horizontally for 5 seconds. Bingo! The slope images on the horizontal axis are the time or frequency. Therefore, if we increase the input sinusoidal jitter to be 10 times higher in frequency, over 1/10 of the time duration, the existing CDR design cannot track it well and result in a limit cycle. Again, the phase error is almost 10% UI, and keep this in mind for now. What else impairments of the CDR can cause the through limited? Think about the loop delay images for 5 seconds. Right, as you can see, the band PD may have latency to decide if the phase of the output clock is earlier or later than the phase of the input data, and then send the early or late signals to the charge pump and loop filter to control the phase or frequency of the VCO to be faster or slower. If the loop delay of the phase tracking is too much, then the lag of the phase correction will not correct or track the input phase quickly. Therefore, it's clear that the limit cycle will also occur during a long latency of the CDR loop here. Again, if we make 100 times the original CDR latency and the phase tracking image from the simplified dynamic model, not only shows the limit cycle, but also provides the phase error could be up to 10% UI. Please be advised that this phase error is just an example of the specific value of a loop latency. With other values of loop latency or even other settings, the dynamic behavior could be much different and the phase error could be even worse. We'll describe the latency of the band CDR deeply in another video later. Here are the summarized images of why we need a band loop dynamic analysis or phase tracking modeling in a band CDR design. To analyze the CDR behavior easily, we either already use a linear phase detector PD or must linearize a nonlinear PD such as band, such that we could provide more insights into the CDR design parameters. Unfortunately, every delineation approach assumes small signal approximation has a big discrepancy from the real large signal and nonlinear dynamic in the band behavior. On the other hand, there are lots of design parameters in the CDR design, and it's impossible to run all the time domain simulation in SPICE. Therefore, a simplified phase tracking modeling in the time domain is a must to receive the band loop dynamic images quickly. The ideal phase tracking image shows a design target, but a few caveat images like the limit cycle or through limited could still happen, and we need to watch out for the band modeling. For example, first, we could end up with a less band step size than what we thought in the circuit implementation over process, voltage, and temperature. Then we could evaluate what the impact of the phase error could be. Second, in some protocols, the amplitude or frequency of the input sinusoidal jitter SJ could be specified as big, and then we should evaluate how to enhance the band step size or the bandwidth to be big enough to track the SJ from the multi-protocol input source feasibly. Lastly, any circuit impairments such as the loop latency, input noise, clock jitter, supply noise, etc. in the band CDR would also degrade the phase tracking ability and cause a big phase error and big array. So we should show the loop latency impact on the limit cycle over phase error from our modeling. Again, we will provide more latency impacts in another video deeply with a more refined modeling close to the real circuit images. Then we plan to include the circuit noise in the modeling to complete a more precise system link budget in another video. Thanks for watching. Before you go, if you are benefiting from raw circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may be benefiting from it.